Hello everyone, good morning. It is currently 9:52 a.m. So again a bit behind schedule, but yeah, I was eating breakfast and I woke up late, and also my mouth is still like hella busted, which is annoying. But let's get on track today. Let's yesterday as I said yesterday, I spent way too much time on just like learning, and I think we need to spend more time just actually building. Learning is still very important, right? There's this piece by Richard Hamming which talks about, you could be in your room and you could be working on your thing isolated for 5 years, right? And you can make like a lot of progress by being isolated because there's no interruptions. But interruptions give you a signal on what is the thing that's important to work on, right? And so by reading and by staying up to date on literature, it sort of gives you a sense of what are the important things to work on. That being said, you want to find this balance, right? So you don't want to get too much signal, or you don't want to spend too much time extracting signal because the process of building that needs to mostly be built by on your own, right? And so um, the purpose of doing these things in the morning is so you get signal, also get some basic knowledge. And I've been particularly interested with role models and how we apply these. Uh, so conceptually, what is a role model? It's essentially it's a very like loaded term, but in my mind, what it is just a model that gives you the dynamics of yeah, well, a model that gives you the dynamics. Basically, you give it a state and an action, and it will tell you what the next state is, right? And why it's useful is, like doing things in the real world, right? Like, let's say I pick up my phone, right? And I'm trying to understand what's going to happen when I like apply force and lift it up. Um, if I did not have a world model, which is like all these model free RL algorithms do, is like, okay, I don't know what's going on. I'm just gonna like query the environment, and then I'm gonna like bootstrap, right? I'm gonna update my queue and my value functions to estimate. Okay, if I do these series of like actions, what is going to be my return, right? It doesn't learn any understanding of what the world is actually doing, and yet somehow it works, right? It works because like you've stepped through enough states, and you sort of like have this universal like value function that's like has seen a bunch of states, and it has a pretty good estimate of how different actions behave, right? So I think that's not enough, right? What we really want is like our models to have an understanding of how the world behaves. And if you look at the LLMs and VLMs, right? So LLMs don't have any physical understanding, but VLMs are starting to, right? If you look at like the latest Genie models. Also, I'm in the wrong account. Let me switch the account. Yeah, if you look at the latest Genie, oh, why am I still logged in? Sign up. Genie model. Alright, these are really, really capable. In these cases, like, we're talking about a state. The state here is just the
With
image.
Genie 3,
And you can think of like the prompt as sort of the action of like how you steer this role model. Yeah, see, that's why I was saying like role models are pretty wishy-washy, because like any video generation model can be seen as like a role model then, right? What's really cool about this is like this is essentially like interactive, right? So you can ask query it to look left, and it will generate in the left direction, right? And it's insane sort of like what they're able to do. So I think this direction is extremely promising. And if we can somehow equip our models with these role models, like our VLMs and our LLMs, or sorry, our VLAs, like what we do in robotics, right? How do we like take these capabilities and pass it to like our robots, because that's going to be really, really crucial, right? But we need to take a step back and sort of understand what has been done in the world model scene. And so what we're going to do is look at Dreamer, right? Dreamer. So even before Dreamer, there was this paper. I keep forgetting the name. Yeah, if you just search the original world models paper, what this paper was doing, and this when was this released? Like 2016, 2015, 2014? Oh, 2018. Okay, right. It's like really, really simple, and I'm gonna quickly go over this because this I actually understand. So there's three parts to this, right? The first part is like encoding. So this is both a world model, and it will be able to it needs to understand the scene. It's going to need to be able to predict the future, and it's going to be able to act, right? So understanding it is simply done through an autoencoder. So you're going to take the original image and you're going to compress it down into some latent representation, and then you're going to use this latent representation to predict the future frames. Okay, so there's a nice diagram here that will show this case, well, how this is done. Right, so it goes through this autoencoder, and once it's in latent space, it goes through this RNN, right? The autoencoder is just like a multi-layer perceptron. I assume it's like some CNN, like there's some convolution layers here. And then once it's in latent space, we use the latent space to predict. So like, what are the next time steps? So this is their RNN, right? And then we have a controller, which is a simple multi-layer perceptron that learns how to like act, right? And what's really interesting is like after you do all of this, you can remove some of the different, right? So for example, what you can do is like you can generate new scenes, right? And so one is, okay, you can play around with the latent representation, the Z, right? So these Z values, like depending on what it is, you can reconstruct it through the decoder, right? But the model itself does not need, like if you look at the actual architecture, right? You can just use the Z, like keep it in the Z representation. So action, it can sort of like imagine its own. I think this diagram. Yeah, this diagram, was that the diagram that I was looking at? Yeah, I think this was the diagram. Right, so you take some action. A controller takes the action. And yeah, I don't remember this part. Maybe the paper does a better job. Alright, so it takes history and then yeah, I feel like they didn't draw it in the diagram because the action also goes to the memory model. And right, because if you look here, all right, this is the M module. And the M is actually what's going to predict the future. Right, so the vision module is like, yeah, encode it, then it's predict the future, then act, right? And for how you predict the future, the crust of it is just an RNN, right? And it's going to take a history of observations, and it's going to take an action, and then predict what's the next action. And then the MDN, I don't know what that is. I'm gonna make sure then it's yeah, the world models paper. To make sure density network, okay. I guess like this is how it's trained, but there's certain components of it. All right, so it goes to the VAE, goes to here, and then the controller takes some action. And it spits out like you can swap out the environment in its own world, right? Model only. Yeah, this is the architecture, right? Or like the high level of like how you would use this world model, right? So you, let's say you actually have the original environment. You take some observation. You can encode this into latent space, and you don't need the decoded version of it because you're using the Z representation. And then your memory module will take this latent representation, will take a history of actions, and it will predict the next uh, the next state, which is going to be used by your controller, I assume. And what's interesting is like things to point out. All three. Yeah, I'll do that. Yeah, I'm a little confused on how Like, which H is this? It's sort of like wishy-washy. Good, but there's some hidden state. Yeah, I just think it's like really interesting, like these sort of like things that they can do. I think it's so cool. I'm gonna ask some questions because I'm not sure how they train. My mouth actually is starting to hurt again. It's fucking annoying. No, teacher voicing is a very common term. Mm. Yeah, so I do think it's yeah. Yeah, I get it. So yeah, I was confused on the z of t and t plus 1, right? But this model outputs h of t and z. Um, yeah, it outputs h of t. Z of t, I don't know where it comes from. I guess initially it has no hidden state, so it'll be empty. But the next time it will have. Yeah, I guess this is a little confusing. Yeah, I think this is good code. No, what the fuck? Like, why did they do it that way? That's what I'm confused about. How can it needs the current action to predict the next history, right? So like you can't just like do that. Yeah, okay. I got it. Does that make sense, guys? So what I was confused about is, you know, the in my mind it was like, okay, it goes through the VAE, gets a latent representation, then you go through this RNN, and then that will give you like a history, a hidden representation that you feed into your controller. But the issue is that your RNN, right, what it does is it takes a latent representation that's like encoding what your current space is, and it will take like an action, right? And based on these two, it will predict the next latent space, right? And I think, is there an image for like, all right, so yeah, you take this this MDRNN, and it's gonna take a latent space, and it's gonna take an action. It's gonna predict the next latent space, and it's also going to you know, have this hidden h of t, which is the hidden state, right? And it passes hidden state, and the controller is gonna use this hidden state, and it's going to update its hidden state based on that. But the controller, it's not going to take the output of the hidden state. It's actually going to just use the hidden state of your RNN at the moment before it takes the forward pass, right? Because this MDRNN, to take the action, the controller needs to like do something first, right? And so that's why you actually take the controller first. So there's like, it seems to have this circular dependency. The controller needs the RNN, and the RNN kind of needs the controller, because that's like, how do you get the action? But there's no circular dependency because we use the controller first, and initially, the initial hidden state of the RNN is just empty, right? And then we're gonna do a controller, take some action, and so you can think of it as the controller doesn't actually see like the future, right? Because it sees the past, but the hidden state is like a useful representation of like what's actually needed. And so to accept the VAE, go through your controller, get an action, and then the MDRNN will predict the future state and update its hidden state, right? And then that will directly update. You step through the environment, and then again you get a latent representation, and and then you re-update with the correct hidden state, right? So you might worry that there's like compounding errors. Because you predict some hidden state, and so that should be actually what the environment hidden state gives back, right? But there's some mismatch. Or is the teacher forcing? Huh? So how does teacher forcing work here, right? So it needs to predict the next vector space. Yeah. So what does a teacher forcing actually do? Dude, I don't want this. Yeah. Oh. Alright, so we get the world models, right? I just needed to clarify what's teacher forcing. So teacher forcing is just this idea that when we train this RNN and we, what it takes in is a latent representation ZT, give output by the autoencoder, right? And then it also takes an action, and it will predict the next hidden state, right? But and you keep doing this, but at any point do you, so for you start from like an initial ZT, right? But if you actually look at what's happening is like it will always take the Z from the environment. Like it might be off, right? And like really it's predicting ZFT, right? Like these are going to be useful because these are not fed into the RNN model itself, right? You actually use the hidden state. That is sort of the thing that's passed to itself. But this part is going to be used later to let it dream on its own, right? I guess like you need to be just familiar with how LSTMs work. Where is Cola right now?
And in fact, even the combination of networks are evolving. The type of applications, the things that you can teach a network to predict artificial intelligence. Today, the unit of pressure is Pascal.
Modules together, the networks learn how to work together and adjust each other in order to perform best at.
Here maybe would contain all of the best middleware.
Okay, so it's just some hidden state. started to hurt. Okay. All right. So you use the hidden state, which is some loss representation, or like some lossless, some representation, of the current state, that's useful to predict the next state, right? Because that's the thing that you're predicting, and you pass that into your controller. Okay. So that's world models. I just spent some time right now to just like make sure I understand RNNs. But we can move on to Dreamer. And Dreamer to Control was came out in 2 years later in 2020. And learning behaviors by latent imagination. So I have not read this. From pure latent imagination. And so the world models paper we were looking at was not using any RL, right? It was just trained on some rollouts. Like you can like it didn't have any concept of words, right? Like it simply just predicted the next state with the world model and then uses controller. And I guess it saw like expert demonstrations, right? Which is kind of cheating because all these other methods don't. But it's like some random rollouts, I think, right? I guess it is RL, right? So yeah, there's some details I actually didn't understand that I'm missing.
Condor Airline.
Thrifty kitchens.
Derivation of the CF.
Search for
This guy's line of work is really interesting. This guy's crazy. Dude, my mouth is like Busted. That's hilarious. This is so funny. I just noticed. Dude, I look like Bart Simpson. Or like... I look like I have like a... This is so funny. Okay. Wait, yeah, lock in. Okay, it's what, 11? Alright. Wait, we haven't gotten to Dreamer. Okay, we saw like Danny was like, or Danijar. Danijar? Very cool. Very like cracked guy. Is he Canadian? He better be Canadian, man.
And a value network from imagined sequences of compact model states. The actor is updated efficient components that can be executed in parallel. From the dataset of past experience, it learns a world model. Using the world model, it learns behaviors in imagination using an actor network and a value network. The actor interacts with the environment to grow the dataset of experience. Let's look at these components in detail. To learn successful behaviors, we need to learn a world model that accurately predicts future rewards. To learn this world model, we draw a sequence of images.
Hi there. Today we're looking at the final result. You encode your state, get input. It goes through the hidden state. You can learn a decoder that reconstructs that observation. It means it can to do this, of course, then we can take actions. If we can make over this tau
actions and rewards from the dataset of past experience. The images are encoded using a convolutional network. Given the embedded images and actions, a recurrent neural network predicts a sequence of compact model states. These automatically learn to represent concepts that are helpful for predicting future outcomes. From each model state, we then predict the corresponding reward. We also reconstruct the image to facilitate representation learning. Predicting ahead using compact model states instead of raw images lets us efficiently predict thousands of sequences in parallel on a single GPU using a large batch size. Moreover, the compact model states learn features that facilitate accurate long-term prediction, as shown here for two environments. For 5 input images, we first visualize their reconstructions by the world model. Given future actions but no further images, we then use the world model to predict a sequence of future model states. For visualization, we reconstruct these states back into images, revealing accurate video predictions for 45 steps or more. Using the world model, we want to derive behaviors from it. We use 2 neural networks for this. An actor network is trained to predict successful actions. And to consider rewards beyond the prediction horizon, a value network estimates the expected future reward of each state. Here is how we learn the 2 networks. We start by encoding past images to obtain a set of initial model states. Using the actor network to select actions, we then predict a sequence of model states. For each model state, we predict the corresponding reward and value. To improve the actor, we backpropagate these rewards and values through the sequence of model states back into the actor network. To differentiate through stochastic states and actions, we use reparameterized samples or straight-through estimation. The value function optimizes Bellman consistency. That is, the value at each state is trained towards the reward plus the value at the next state. Having access to the world model, there's no need for Q-learning. These are some of the behaviors learned by Dreamer, given only images shown here as input. The top row shows a range of challenging control tasks with continuous actions. The bottom row shows visually more diverse tasks with discrete actions. These tasks pose a variety of challenges to the agent, including highly nonlinear dynamics, many underlying degrees of freedom, and 3D scenes. We empirically compare Dreamer to existing methods on a benchmark of 20 continuous control tasks with image input. Instead, both exceeds the highest reported performance on this benchmark, that of the advanced D4PG agent, that was given 20 times the amount of environment interaction. In summary, Dreamer outperforms previous model-based we found on the project website.
Okay, let's read it. Maybe I do need Yannick's video.
In this case, they want to learn policies for these kind of continuous control tasks. So these physics-based robots, these hopper or walker types of tasks, where you have to control this robot, these joints, in order to move forward. And so the goal is that you have multiple observations, as you do in reinforcement learning. And from each observation, you need to somehow come up with an action of what to do. And then that will give you the next observation as well as a reward. A reward for, you know, if your goal is to move this spider, maybe the reward is proportional to how far you move. So your goal is to collect the maximum reward, which would mean you have to move the spider as far as possible, simply by doing the correct actions. The goal of this paper now is to do this by learning to sort of plan ahead in this latent space. So as you can see here, the way they do it is they take the observation and they feed it through an encoder. Now you can think of this as maybe a convolutional neural network or something, anything that can work, that can take an image as input and give you a hidden representation. So now this here is the hidden representation. From this hidden representation, you can determine what the next action is going to be. And then you...
Imagine being able to build an app with your name on it, just by base 44.
Get a new observation, and then again you can feed that, else we cake, and then you always... Now my encoder tells me that this is going to give me this hidden state. And now what it wants to do is it wants to take in the action, the red, and then this now thing are an accurate representation and a transition, and let's say
Yeah, I think
a
I might as well
reward.
just read the paper.
So
to be
you also
honest. Might as well read the paper. Paper is source of truth. representation model is transition model. Okay. D4PG. So it's good to familiarize yourself with these people. Okay. Well, it's on my reading list. How many papers do I have right now? And am I on track?
Side. Danny
Locked in. These guys are too like research grindy, man. You gotta have some real world experience, guys. Damn, the Walmart rabbit hole is like quite a big rabbit hole too, huh?
guess this is, in a way, you're...
is that we really want to believe that all of the knowledge
Clearly, Dave needs no introduction, especially here. Really poignant for me.
Themselves that could discover that uses the standard libraries. It's probably been optimized by AlphaDev. Fusion, which is, if you scale all these things up, you get incredible results. And this is a proven recipe. So I am going to quickly take a little aside just to talk about this discovering RL. Even though I think it's a little bit of we were using deep reinforcement learning, the idea that we were doing gradients of the box, it also beats the state of the art in those held out environments, things like PropGen, DMLab. And what's nice as well, in an agent's path through that world, it will only encounter a tiny, tiny fraction of the potential state methods which are hallucinating all the time. And to me, these brilliant mathematicians selected from each country, six from each country at the end, and many of those go on to become great mathematicians later. In fact, 50% of all Fields medalists were IMO competitors. And at the end of that, there's this medal ratio that's allocated to the competitors in the ratio 6 for no medal to 3 for bronze medals to 2 for silver to gold 1. So that's about 7.5% of get a gold medal of these brilliant mathematicians. So just to give a flavour of what do these look like, I put up one problem. This is what they're.
If someone was to make a fully functional data, and the data isn't particularly structured, it's like whatever examples, for example, from the internet. So I just don't think this is playing to quantum computing.
Probably the problems, and they have made no headway on the IMO as from that data, which proofs are effective. And that allows us to go from, say, 100,000 approach was simply to mine a wide range of problems, formalize them in a bunch of different ways, line up the proof. And what that does is when you apply this tactic, it updates, really learning to get better and better and improve and improve and improve. So now I want to come back to the idea from my PhD thesis. What do you do when you now are actually entering the competition? We enter. Okay, those are all bogus for very similar reasons. It isn't one of the original points in the original problem, shown in black here, and comes up with this very beautiful construction. Sorry, I should say the B4 solution. I also want to show one of the failures of the system. So this is a combinatorics problem, which the system did not solve. So this is problem 5. A lot of the humans were really unhappy with this problem 2, by the way. But I would say, it shows what is so hard about these kind of problems. So I'd say it's almost perfectly designed as an anti-computer problem, where it's essentially the problem.
Legend.
So many on reinforcement learning. It's clear. I wasn't sure, but now I think it's clear. This was the right move today. And, we need a conference on reinforcement learning. It's clear. I wasn't sure, but now I think it's clear. This was the right move. So I have prepared for you a talk on the oak architecture. It's a vision of superintelligence from experience. It really is my attempt to address the issues at the center of AI. And I want to, they're still ahead of us. It's a marathon. I think, it goes for this group that the path to full AI, strong AI, runs through reinforcement learning, and not, I think, through things like, to non-experiential things like large language models of understanding mind. Okay, so those are my introductory comments. Now let's talk about oak. I think it's fun just to start with a name, which may be a mystery. Oak, it comes from the idea of options and knowledge. Now, as many of you are very familiar with, an option is a pair. Well, actually, you may think it's a triple. I sort of dropped the initiation set in my behaving. But let me just put down my 3 main So it served different purposes. For me, actually, it almost fits on a slide. You write in the pseudocode, has all those things, but it also adds auxiliary subproblems, and those but has the consequence that, okay, and the interesting thing about planning with option models is that it's the same. It's really the same. Can't do that, of course. We have to have functional. That would just be a really big thing. And I think there's no reason why it couldn't happen, and so I think it will. I also think that something like my algorithm called IDBID, or IDBD, and it's really old, will be a key part of that, solving this problem. Okay. I'm sort of done with computational theory of intelligence. Okay, now what about someone like yourself?
Thank you. In reinforcement learning, we encoded in math because math is precise. And so for many years now, decades, we've looked at value as being this expected sum of rewards over trajectory of state, subject of policy. There's a look at variance on this one, but that's roughly, I hope, like that is the question at the entrance door when you get into this conference. What is value? And now I'm going to ask you to let go of that as you walk outside of that door. And so when you look in other fields in economics, the notion of value is really defined in terms of like the worth of a good, worth of an outcome. You get into this defined in terms of actions, honesty. Completely, this notion that values are created. How do we formalize what is valuable? That what we are. So let's enter it on familiar grounds, classic Bellman. What do we know about that? I'll have a chapter about sort of extending timidity. So let's start on familiar grounds, still early morning. Bellman gave us this wonderful equation. And frankly, this is possibly like the single equation that made me fall in love with RL. There's an elegance here that has guided my professional path for 30 years now. And what's so elegant about this is that it gives us a simple way to turn planning of what we try to do into computation. If you compute the value, then you get the answer to how you should behave. And there's something profoundly inspiring about that. The challenge when you fall in love with an equation is that you sometimes forget all the things that are underlying that formalism. So here we have it. Underneath the hood of that, there's a Markovian assumption. The fact that, of course, you simple law. So that's all. Why I'm bringing this up is as we're moving forward, this value function in many ways has been the soul of RL. It's a central abstraction that permeates so much of our work. An RL researcher, how's your value? How's your value? We shake hands, we know what we mean, right? This is not necessarily comfortable to get outside of that. And it also gave us our unique language compared to other fields, whether it's control theory, supervised learning, or others. And beyond that, it's not just comforting. It's not just about being in the cult of RL. This is about making progress together. Having a common formulation means that we could build on the same abstraction. It means that we could have the same benchmarks, and we knew what we needed to measure to make progress. We knew what to compare. And also, as much as possible, we could make advances that were formalism. And while value function unified our math, it unified our community, it gave us a lot of as well. And at the time, we were somewhere, I might pull this graph, around 2018, I think, when we were doing some of the early work on reproducibility in RL. And at the time, we were somewhere around like 30,000 papers a year on RL, and I pulled the numbers again like last week, and like suddenly we've seen a huge rise. And so 180,000 papers that discuss RL on Google Scholar. And I think sometimes the last few years they'll have to catch up. Takes a little bit of time, so I don't know if it's like a definite decrease or it's gonna keep on increasing. We'll have to see. But nonetheless, like clearly there's a lot of interest in this field. There's a lot of people working in this field. So we also have potential to explore many more ideas of what it means to do RL. And so let's take this to the next chapter of how we might timidly extend the Bellman formalism, and sometimes to really great benefits. And so I'll sort of talk about a few phases of the field. We had the classic RL period where we were really looking at very specific individual tasks of how to and the ability to use RL to optimize. In more theoretical domains, I was quite happy to look at the classic Bellman formula, the types of groups that have done work in this area. This is just one sample of it. The safety work from these that people can access between these different properties, and quite how that values is defined to be still enough phase. If you're interested, please look into it. An amazing lineup of speakers and papers. Familiar for many parents. We've all decided to abide by the authority of that. And satisfaction, where we're actually imposing the values in terms of what we solicit from the humans. How do we live in a world where we have today, when you're prompting stand for in the work that we do? So we picked 6 of these values back in 2017, and through that time, the field of research changed incredibly, the organization changed incredibly, but we were able to maintain a consistent set of values. Out of these, probably the one that is most the signature of this organization is the openness, but the others were there, and I assume are still there and caring how the work gets done. Let me talk a little bit about openness, because it was one that was very much near and dear to me. And over those kind of 10 years or so, it allowed us over that time to release over 1,000 different research artifacts from the work that we did at a time where this notion of openly releasing research was not necessarily the modus operandi for many other industry labs. And I do think that encoding it as a core value of the organization and communicating about it consistently helped us keep that path open. And so sometimes being explicit and stating what your values are helps you build a strategy to realize those values. And you can do it at the scale of like a reward function, but you can also do it at the scale of 100+ person organization. One of the things that's interesting when you do that is that you also have to look at the broader ecosystem. And so because FAIR was a research organization that operated within a large for-profit corporation.
Dude, that's where I went. she did side. Interesting.
You have to build bridges between the values of these organizations. And one of the ways we did this is being very explicit about articulating in what way does this bring economic value to the company? What does bring brand value to the company? Knowing that these are farming and so on and so forth. Tons of example of people who are solving problems in their own communities in ways that matter to them. So sort of closing the loop on this notion of pluralistic values, that when you share those artifacts openly, it enabled this pluralistic value to exist. There was no way that necessarily a large US corporation was going to devote the resources to doing that, but it was going to build a model that served its own purpose and then could share it with others. Now, it's not always that easy, and sometimes there's a real tension between your values, and as much as, I love to doing that, but if you can clearly identify what are the threats, if you can measure those threats, it's easy.
Yeah, it's not very useful.
All right, so yes, online fine-tuning from offline initialization. So offline are basically algorithms that just train on the data. Online fine-tuning takes whatever you got from the data. You have a pretty big problem. And I can say for sure those assumptions are necessarily correct. But the implication is there. The implication is that something about TD updates is not as wonderful for representational learning as supervised learning is. And in fact, other works have corroborated this high-level idea, although they postulate different mechanisms for it. The pictures that better align with what we requested. So we're going to have the following system. We're going to have our diffusion model. Is that some prompts are easier than others, and the easiest two-sentence summary is this. We have to learn the bitter lesson that building and how we think does not work in the long run. The two methods that seem to scale arbitrarily are learning and search. Now, some people read these sentences, and they come away with the conclusion that this means we need to show more data into views. That's not a bad conclusion, by the way. I actually fully approve of that statement, but the essay says a lot more than that. And you'll notice that there are two words, learning and search. And I guess we all know what learning is, but why is the word search there, and why is it placed on an equal footing? Well, because it's really important. So here's my interpretation. Learning is about using data to extract patterns. You go out into the world, you grab your data, and you figure out what's going on in the data. What are the patterns? To me, what search means is doing some additional computation to analyze optimization. So we really need is a combination of data for immersion behavior. And that's the lesson I took away from that essay. Maybe I got it wrong, maybe I got it right, but I kind of like that lesson. I'd like to thank my students who carried out much of this research. I'd like to thank you all for listening.
Go ahead. Thanks for the talk. So I was thinking about the correlation that you're talking about when you're TD and I was abstract representations. And there's this other line of work that there are a couple of papers that have really points that's really two states that are. So do you have any thoughts on that?
Yeah, it's a really good question. I don't know, and I do think it's sort of like the classification loss thing is mysterious, and the representation history is mysterious. A few things are mysterious, and they're probably related, right? But yeah, the truth is I don't know. The dot product thing does happen with other losses, so that's not just a squared error regression problem. But the cross entropy loss seems to help, so maybe it has something to do with it. Certainly makes training big models easier, but I don't know why. Great question. So in fact, there is a significant body of work.
All right.
Emulator, you can often sort of teleport into an emulator.
Dude, I need to go to this RL conference. Dude, I missed out. 2024? Where was this? In Amherst, Massachusetts? Damn.
Policy that was being selected from this process, that sort of algorithm hyperparameter, that was far better for the same amount of a 12th grader, it could do a decent job. You could do something that was plausible. But the next thing that we asked it to do should be an easier question. So on the right-hand side, we've got E and help do the same. They're like, okay, all of those worksheets are pretty similar. I can't. And the question is, what data should we gather in order to learn a good policy? So I'll be a little more precise. We're going to try to think about a really small scenario here to think about characterizing it formally, but I will motivate it.
For reinforcement learning AI scientists, I would hope it's task of AI. So since they all have to be capable of being done at runtime, why not make a conceptually simple design? It just doesn't worry about trying to get a head start on the problem. It just has.
All right, welcome back.
more maybe, but, and the title, I came up with, that'll be why that title will become apparent in a while, but I'm going to start with just my personal experience, and then look at some more historical things. So to begin with, to me, this is sort of my personal view of what RL is. It's a combination of search and messaging simulation. It was called, I forget what it was called, but so that was the University of Michigan. I was an undergrad there too. I majored in math, implements a law of effect, and Chuck wrote the code for this. It was the same network, but it was trained with super. And this hypothesis, I think, is still a mainstream hypothesis in neuroscience about how the dopamine system works. That the dopamine signal is not a reward, but is as an example of how you have to be careful what you wish for. So what you wish for is kind of like, what is the reward signal? And his story is that I think it's a classical horror tale. It's a classic example.
Well, we got this fantastic thing here. Specific things that you might have gone direct inspiration in your work.
Okay, great, thank you.
So thank you for your talk and planting the seeds from which this community grew. You mentioned in your briefing to be careful what we wish for, and also caution to remain focused in part on classical methods. And my question is, what if we do not heed such advice? That's some of the ramifications.
Well, it opens you up to someone saying, oh, why did you use this that's been around for 30 years? It does better than your algorithm. You know, and I always wanted to avoid that comment, but it's quite easy to show something using RL and some person say, what are you doing? Oh, well, we do that this way. And sometimes that's true, and sometimes it's not. So I guess, yeah, I don't know what else to say. Does that help answer what you're after?
It does.
Okay, thanks.
I really appreciate your historical perspective. I really appreciate your historical perspective on the field. I think something that surprised me.
It's sort of.
I need to find the best way to learn math.
In the late 1940s, learning.
When I was
and Richard Sutton, the 2024 ACM AM Turing Award recipients for developing the conceptual and algorithmic foundations of reinforcement learning.
When I was an undergraduate at the University of Michigan, I stumbled upon a little book in the library called Brains, Machines, and Mathematics, written by Michael Arbib, and I was impressed that maybe I didn't have to choose one of those to study. I could study all three. After I received my PhD, I heard of a postdoctoral position at the University of Massachusetts. They had a project that was initiated by a physiologist named Harry Clough, and he had the idea that theories of intelligence were wrong. And I was hired as a postdoc on this project. I don't know how long after that Rich Sutton came as a graduate student.
I was at Stanford. I was reading everything in the library about artificial intelligence, trying to do learning, and learning was totally unpopular, out of fashion in AI. And I read the literature, and the literature was a little bit unsatisfying because it all kinds of supervised learning, but it always seemed to me there should be something more. And it was obvious from the point of view of psychology that there should be something more. Finally, I found Harry's report. Totally just an undergraduate student at Stanford. He's this guy who wrote the report that I found in the library, but I guess I was brash enough to just write a letter. All kinds of supervised learning, but it always seemed to me there should be something more. And it was obvious from the point of view of psychology that there should be something more. Finally, I found Harry's report. Totally just an undergraduate student at Stanford. He's this guy who wrote the report that I found in the library, but I guess I was brash enough to just write a letter. Anyway, it all worked out within a year. I was in Massachusetts with Andy.
So machine learning people study several different kinds of problems. One is called supervised learning, which is learning from late learning, is different from both of those. The examples are not evaluated by, say, a reward or pleasure, if you will.
It's like night and day. Supervised learning, it's like you're memorizing cue cards. Someone's giving you the answers, you have to just remember them. Self-directed learning, reinforcement learning, the agent has to figure it out and has to try things and figure out what's the right one. Much more powerful process. That's what intelligence is. Intelligence is figuring out how the world works, rather than waiting for someone to tell you how the world works.
In those early days, there was a lot of thinking along the lines of reinforcement learning. Minsky's thesis, there was also the famous Samuel's checkers player. It was a reinforcement learning system. You know, it was our concern with history that really enriched the kind of thing we were doing, and we felt like pioneers because those ideas had kind of been abandoned. We thought they were abandoned prematurely.
Maybe it's obvious to everybody that learning is an important part of intelligence, but strangely, it wasn't obvious to AI researchers at that time. All the animals, if Andy Barth was here, he would tell me to be careful about my superlatives. Almost all the animals have classical and instrumental conditioning. These ended up being the two things that we formalized as engineering endeavors. Instrumental learning became sort of what we usually think of it.
Is using what you know, or what you think you know. That's exploiting your current state of knowledge. But it's maybe wrong or incomplete, and so you need to explore because you may learn something to augment your so-called knowledge base. So these reinforcement learning systems do that. In fact, they use randomness to try things. You know, it's a trial and error process.
The biggest impacts of reinforcement learning have yet to come. Probably the biggest one that has come would be AlphaGo. I remember watching the Go masters at the time analyzing the position when AlphaGo made that move, and they said, ooh, that's a mistake. And over time, it became clear that it was actually a really good move.
I mean, one thing that I think was very exciting, the same algorithm is related to dynamic programming, which is what Rich Sutton's thesis was about. But that algorithm is very closely related to how the brain's dopamine system works. And I think now this connection to the TD algorithm has actually heavily influenced the neuroscience of mammalian reward systems. And so we explored this idea and came across a lot of things that were surprising. Then we wrote a bunch of papers, some of which were good.
Looking ahead, there's the opportunity to fulfill scientific method is our attempt.
It's so cool. Wait, guys, I'm getting sidetracked. There's so much in this RL space. Okay, I'm gonna stop here. My goal is to understand world models. Did not get super duper far. I will continue this tomorrow. Yeah.